sinusoidal signals. A continuous time signal, sinusoidal signal, can be expressed as, already we have seen these sinusoidal signals in the last video. X of t equal to a cos of omega naught t plus theta, where a is the amplitude real, w naught is the radiant frequency, w naught, sorry, omega naught, this is the omega naught, radiant frequency in radians per second unit, and and theta is phase angle in radians. Theta is the phase angle in radians. The sinusoidal signal x of t is shown in figure 1.9. Continuous time sinusoidal signal. Here in x-axis time, t in time. In y-axis amplitude, x of t, here mentioned amplitude a plus here, a minus. This is a cos theta 0 here. In between peak t naught equal to 2 pi omega naught. Here the sinusoidal signal x of t is shown in figure 1.9 and it is periodic with the fundamental period. It is periodic with the fundamental period. Okay. The reciprocal of the fundamental period t naught, the reciprocal of the fundamental period is called the fundamental frequency. Is called the, that is 1 by t naught in Hertz. Okay. This is the fundamental frequency. From equation 1.38, this equation 1.38 and 1.39, we have omega naught equal to 2 pi f naught. This one. Actually, f naught equal to 1 by t naught. So omega naught equal to 2 by f naught, which is called fundamental angular frequency. Omega naught is the fundamental angular frequency. Here t naught to show in here, t naught is 2 by omega naught, which means from start here to up to here. Up to here, t naught equal to 2 by divided by omega naught. Okay, this is a cos a plus a minus x of t. Here 0. This is x-axis. X-axis is the time. Y-axis is the x of t, function of t. So, which is omega naught is the fundamental angular frequency using Euler's formula. The sinusoidal signal 1.37 can be expressed as a cos of omega naught t plus theta equal to a re that is ra denote for Re denotes real part of, and we also use the notation Im for to denote imaginary part of. So A cos omega naught t plus theta equal to A Re set of e power j omega naught t plus theta. A imaginary part of e power j of omega naught t plus theta equal to a sin omega naught t plus theta. Here continuous time sinusoidal signal. Here in the sinusoidal signal, here this is second side, that's why minus a amplitude, here plus a amplitude. This is x of t from peak value to another peak value equal to t naught up to here t naught, that is equal to 2 by divided omega naught. Omega naught is the radial frequency. Sorry, fundamental angular frequency. Fundamental angular frequency. Basic discrete time signals. Unit step sequence. Figure by 10. Unit step sequence. A, B, shifted unit step sequence. The unit step sequence. The unit step sequence U of n is defined as U of n equal to 1. The condition is n is greater than or equal to 0. Another one, U of n equal to 0. The condition is n is less than 0, which is shown in figure 1.10. A. Note that the value of U of n when n equal to 0 in x-axis n, y-axis y of n, here 1, here 0, here 1, here 2, you can see so on so on. N here minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, and so on. N equal to 0 is defined here, this part. Defined unlike continuous time step function u of t at t equal to 0, not like a continuous time step function u of t at t equal to 0, and equals unity, equals because here all are equals unity. Similarly, the shifted unit step sequence, that is shifted minus 2, minus 1, here unit step sequence, this is okay. Here also minus 3, minus 2, minus 1, minus 0, minus 1, k, that is this one from shifted this much up to k, that one showing here. So similarly, the shifted unit step sequence u of n minus k is defined as u of n minus k equal to 1. N is greater than or equal to k, that is here. Here only u of n minus k equal to 1. Here from here, when n is greater than or equal to k, from here equal then greater. Here n is greater than equal or greater, equal and greater. Here n is less than 0 here, so 0 v of n 0. Here v of n minus k, because y minus k came here, because k times shifted, that's why we are put shifted. Similarly, the shifted unit step sequence v of n minus k is defined as v of n minus k equal to 1 0 n equal to n is greater than or equal or greater than k and then 0. Here when n is less than 0, here full here 0. So here two values there for v of n minus k equal to 1 for here. Condition is n is greater than or equal to 0. Yeah, equal sorry, greater than or n is greater than k. N is greater than or equal to k. Okay. If 0 getting is the result. If n is less than k, then 0. Then the unit impulse sequence. The unit impulse or unit sample sequence del of n is defined as del of n equal to 1. The condition is n equal to 0. When 0, n is not equal to 0. So this is the condition. Here. Unit sample, unit impulse sample sequence shift A, B is the shifted unit impulse sequence. Only impulse only. Only unit impulse only. We will take care. The unit impulse or unit sample sequence del of n is defined as del of n equal to 1, n equal to 0, n equal to condition is when n equal to 0, this is the n in x-axis, n here minus 2, minus 3, minus 2, minus 1, 0, 1, 2, 3, here minus 2, minus 1, 0, 1, up to k here, k. So here in y-axis del of n, here 0, 1, and so on. In shifted unit impulse sequence, in y-axis del of n minus k, because shifted this impulse shifted in kth place, k, that is the here, that one is k. So one is when del of n is 0, when condition is n equal to 0. When del of n 0, that n equal to not 0, not equal to 0 here. Yes. Which is similar, which is shown in figure 1.1 here. Similarly, shifted unit impulse or sample sequence del of n minus k, del of n minus k, n minus k means shifted as del of n minus k equal to 1 when n equal to k, here 0, here k, kth place shifted, that impulse. When 0 getting means not k, here in the kth place only impulse response is 1. Other remaining places other than k, here all are